Welcome, and thank you for participating in this evening's edition of the Department of Energy's Solar Decathlon Virtual Session Series, which will address a virtual hands-on energy workshop for families. My name is Jonathan Cohen, and I run the Solar Decathlon Virtual Session Series with your Department of Energy. First, let me share what the Solar Decathlon is. It is a collegiate competition that consists of 10 contests, which challenge student teams to design and build highly efficient and innovative buildings powered by renewable energy. The competition features 2 tracks, a design challenge and a build challenge. The Solar Decathlon provides a hands-on experience and unique training that prepares the competing students to enter the clean energy workforce. But the Solar Decathlon is more than a competition. It's an intensive learning experience for consumers and homeowners alike as they experience the latest technologies and materials in energy-efficient design, clean energy technologies, smart home solutions, water conservation measures, electric vehicles, and high-performance buildings. Participation since the first Solar Decathlon was held in 2002 has involved more than 465 collegiate teams and more than 23,000 collegiate participants from more than 23 countries. If we go on to the next slide, we will review our agenda for tonight's virtual session. And we actually have only 4 things on the agenda, which is a quick run through of what is coming up in terms of the Solar Decathlon Virtual Session Series, a quick review of the technology that you can use to ask questions of our speakers this evening. Then I'll introduce our speakers and then turn the floor over to them to actually carry out the virtual hands-on energy workshop for families. And the only ground rules are to be engaged and to ask questions, if you have any, as to how you can make the most out of tonight's session. And so with that, we're going to move on to the next slide and share that we have a real great monthly schedule through May with the Solar Decathlon Virtual Session Series. In December, we'll hear from a showcase of student leaders who've done absolutely fantastic projects. And there'll be a series of 6 students, each presenting short summaries of the work that they've done, and it's quite impressive. And then in January, we have a bona fide solar legend speaker in Scott Sklar talking about Resilient Home 411 strategies to weather and recover from natural disasters. And then we'll have experts from the Department of Energy speak in February concerning zero energy ready homes, new and growing fast. And then the department will also present on the future of solar, a tour of cutting-edge solar research in March. And then in April and May, we'll hear from the actual participants in the Solar Decathlon Build Challenge themselves. So let's move on to the next slide and share how you can ask questions this evening. You can either chat in your question through the big red square there, or you can virtually raise your hand in the upper left, in which case we can unmute you to ask your question to our speakers directly. So that will always be there on the side, and we encourage you to ask a question as soon as you think of it while it's fresh in your mind, and then we can make sure that the speakers get to it. So with that, I'm pleased to be able to introduce our speakers this evening. We have a dynamic duo from the National Energy Education Development Project, and we will start by introducing Karen Terrell, who is a Curriculum and Training Associate with the NEED project. Her role with NEED includes training teachers in K-12 plus in energy education and writing curriculum primarily in renewable energy resources and energy management. In 2016, Karen earned her Certified Energy Manager status and uses this training to assist students and their teachers in basic energy audits of their school buildings. A graduate of Michigan Technological University and Indiana University, Karen holds a BS in Biological Sciences and an MS in Secondary Curriculum. She joined NEED after many years teaching chemistry and physics at the secondary level. We are also joined this evening by Barry Scott, who is the California State Director for the National Energy Education Development Project, affectionately known as NEED. And he manages educational programs throughout the state. Barry works with public agencies such as the California Energy Commission and the Department of Education and energy industry sponsors to promote energy literacy and career awareness in public schools. So with that, it gives me great pleasure to be able to turn the floor over to Karen and Barry to take you through our virtual hands-on energy workshop for families this evening. Karen and Barry, the floor is yours.
Thank you, Jonathan. Welcome, everybody. Glad to have you here. I am going to go ahead, and start showing you my screen. Okay. We're going to start with an activity called a Kahoot. If your kids are interested or do this with your teacher, sometimes the teacher will use this as a little warm-up. We're going to use Kahoot as a little warm-up to get you started and having fun. Oh, I have got to make that music go away. Hang on one second. There we go. Okay, so Kahoot.it is where you want to go to be able to play. Is everybody seeing this okay? Barry, are you seeing this okay?
Yep, we can see just fine.
Okay, good. All right, so you want to go to Kahoot.it. Now, here's what I recommend you do. I recommend that you leave the device that you're watching the webinar on the webinar, and then you grab a cell phone or a tablet or something as a second device to actually play the game. So you want to go to Kahoot.it, www.kahoot.it, and then it'll ask you to put in the game pin. 2801212 is that pin. And then as you're seeing, you just throw your nickname or your name in there. And once we get a few more people in here, we'll start playing. And how this works is there will be some questions on the screen, and then on your device, there will be corresponding buttons that you touch to indicate the answer you want to submit. So if it's a true, false, there'll only be two. There'll be a blue one and a red one. And I think blue is always true and red is always false. If it's a multiple choice question, there'll be 4 colors, and each of the colors will correspond with one of the answers. And you touch the one that you think is the right answer. I'm gonna give it maybe 1 more minute. See if anybody else wants to jump in. Go to Kahoot.it and type in the pin 2801212. Anybody else want to join in and play Solar Kahoot? Let's get this going. Okay. I have to move this thingamajig over. Here we go. First question, true or false? The energy on Earth comes from the sun. Only geothermal, nuclear, and tidal energy do not. The blue if it's true, red if it's false. Getting the answers in. All right, so we had 7 answers in. The answer is that is true. Solar energy is the origin of our energy sources. I don't know how to, okay. Oh, Elsie, first place. Way to go, Elsie. Sparky in second. Here we go. This is a quiz, so it's multiple guess. The sun generates energy from a process called, I cannot see these answers on my screen. Nuclear fusion, the Death Star, nuclear fission, or magic. There we go. Nuclear fusion is correct. Nuclear fusion in stars, nuclear fission in our nuclear power plants. Very good. How are we with the standings? Sparky moved up, Kitten Boy moved up, Elsie, bummer, moved down. Okay, let's go. Here, let's do another one. Another quiz. The highly purified silicon wafers used in making PV cells are most often doped with carbon and arsenic, chlorine and bismuth, phosphorus and boron, or only silicon and nothing else? This is kind of a tough one. This is kind of a tough one. 4, 3, 2, 1. Phosphorus and boron. Phosphorus and boron. Barry will be explaining to you why that is. How'd we do? Oh, Kennedy rocketed right up there. Way to go. All right, another quiz question. What energy transformation takes place in a photovoltaic cell? Is it radiant to electrical, chemical into motion, chemical into light, or radiant to chemical to electrical? Ooh, kind of a tough one. Kind of a tough one. What do you think? 3, 2, 1. Very good. Most of you got it right. Radiant into electrical. Excellent. Kennedy's still in first place. Way to go, Kennedy. Elsie, you moved way up. Good job. True or false? Solar energy systems do not produce air pollutants or carbon dioxide. Is that true or is that false? 3, 2, 1. Very good. It is true. They do not produce any pollutants or carbon dioxide. Kennedy's on a hot streak. That's why there's a flame right there. Okay, let's go to our next question. Quiz. The amount of sunlight varies depending on your location, your weather conditions, your time of day, or all the above. Oh, fantastic, guys. All of the above is the correct answer. Nothing changed. Kennedy's still kicking it. True or false? More energy from the sun falls on the earth in 1 hour than is used by everyone in the world in a year. Ooh, more than everybody in a year in 1 hour of sunlight. True or false? That is true. Very good. We're still doing a good job with most people getting the right answer. Some of these are a little hard. Oh, Tia on a hot streak. Here we go. Elsie's still hanging in there. And Kennedy, man, you're still in first place. All right, what are the two types of solar water heating systems? Are they direct and indirect, active and passive, integral and thermal siphon, or radiant and thermal? You have to kind of know a little bit about water heaters to know this one. 3, 2, 1. How'd we go? The answer is active and passive. That was kind of a tough one. Barry will be telling you guys all about those. How'd we do? Oh, Solar Lover moved into first place. Kennedy fell off the first place podium. Oh no. All right, 2 more questions. Conversion efficiency of a PV panel is 1 to 2%, 15 to 30%, 5 to 10, or over 50%. Conversion efficiency of a PV panel, photovoltaic panel. 5, 4, 3, 2, 1. 15 to 30%. Most commercially available PV is like right around 20 to 25%. Very good. How are we doing? Solar Level still winning. All right, we have 1 more question, guys. This is it. This is for all the marbles. Quiz. What is the name of the device that changes DC current to AC current in a residential PV system? Is it the arrestor, the battery, the inverter, or the circuit breaker? The arrestor, the battery, the inverter, or the circuit breaker changing DC to AC? The inverter is correct. Now, if you looked at that picture that was with the question, the inverter was on there, none of that other stuff was. Excellent job. All right, here comes the podium. How did we do? Kennedy in 3rd place. Way to go, Kennedy. Tia in 2nd place. And our 1st place winner is Solar Lover. Great job. Great job. So that's Kahoot. Haley and Kay, you were right there. You were right there with them. So that's Solar Kahoot, and that is just a fun way to get us started. We're gonna leave that, we'll make that go away. We're gonna come here, we're gonna get this started, and I'm going to turn this over to Barry. Barry, take it away.
Okay, thank you, Karen. Go ahead and give us the next slide, please. This is an overview of what we're going to do in the next 45 minutes or so. I'll give you a kind of a solar 101, basic information about solar energy and solar energy generation. We're going to talk about briefly sizing systems, energy efficiency, and then move on into our solar cooker project and the competition. So I'm happy to have everyone here, and let's get started. Give me another slide, Karen, and tell me what that image is. You found it. It's a beautiful picture.
So that image is a composite from the Solar Dynamic Observatory. A Solar Dynamic Observatory is a satellite that orbits Earth, but it's way out, way above pretty much everything, farther out than even the moon. And it always is looking at the sun. And so this is an image that was taken in ultraviolet, X-ray, and gamma ray, and then they added color to it. And the thing about it that's really cool is you can see the different convective zones on the surface of the sun, and you can see the magnetic field lines as they're extending out. I love this picture.
Great. So it's a super hot ball of burning gas. Next slide. And what happens is nuclear fusion. What's going on in the sun is fusion, in which isotopes of hydrogen, which are shown there, deuterium and tritium, are super compressed and fused, and the output is a helium atom and a free neutron and tons of energy that's expressed in radiant energy, largely electromagnetic radiation that goes out in all directions and reaches Earth. You can see that radiation comes to us in visible light, gamma rays, infrared, ultraviolet. And it's interesting to note that it's kind of indicated by this diagram, it's the sun that gives us the water cycle. Therefore, hydropower is a result of solar energy. It's the sun heating the Earth's surface that produces convection currents of wind. And therefore, wind energy is really originally solar energy. And of course, all of our fossil fuels were originally solar energy that through photosynthesis created the plants and the energy stored in the plants and the animals that ate the plants and so forth. And so most of our energy, even if not directly, most of our energy is originally solar energy. Next slide. You can see what we use. We wouldn't be alive, let's face it, without solar energy. And in modern times, what we're able to do around our buildings, since this is a solar decathlon, we can use solar energy directly for space heating, for water heating, and of course to generate electrical power. And there's two different general ways that electrical power is produced using the sun. One is concentrating solar power. That's usually at a large level, not at a home level. And then photovoltaics, which includes anything from a calculator to a rooftop solar system to a solar shaded carport at a school to vast solar photovoltaic farms. Next slide. Daylighting, you know, great architecture always includes a lot of natural light. And where we're able to use natural light, we don't need to use electric lights very much. So that's an obvious choice. It's also a way, when done well, that we can capture some of the radiant heat and even store that heat to keep the house warm after the sun goes down. So daylighting is what's referred to as a form of passive solar use of passive solar energy. In other words, there's no machinery required, it's just daylight. Next slide. And then space heating for passive solar can include a lot of different strategies, including heat retaining walls on the interior. But an architect will always look at the exposure. Where is south, where is north, and may wish to take advantage of a southern exposure and carefully calculated angles to take in winter light, but not take in summer light. You don't want heat gain unless you're in a very cold part of the planet. You'd prefer perhaps not to get any direct sunlight, but you would want direct sunlight in the wintertime coming from the southern exposure. Northern exposure is good for even lighting throughout the day or throughout the year, but for heating, you've got to be very strategic. The diagram to the right further indicates that great care has to be taken to understand the low angle of the sun in the winter and the higher angle of the sun in the summer, and design your home exposures and overhangs and so forth to account for that. And we also show a thermal mass in the floor, indicated in this section on the right, where that sunlight striking the floor, especially if it's a dark color, could absorb heat in the early part of the day and the mid part of the day. And then if it's a thick and dense material, it could remain warm into the evening. Next slide. And when we talk about active solar heating, the difference between active and passive usually refers to whether or not there's additional equipment that may include pumps or fans and so forth. And so you might have a system on a home that includes a solar collector. This could include water, domestic water heating, but also using solar energy to heat water that might produce a solar radiant heated floor by circulating warm water through the floor. Next. This would be a solar collector that would circulate fluid. It could be water, but it could also be other substances that are denser and carry more heat. And you have glass on the outside, insulation, you have an absorbent and a dark material on the inside, and circulating fluid in tubes. You'd also want to include, you'd want it to be airtight, and you'd want it to be insulated so that the heat is retained in these panels, but the fluid is circulated from these panels that are exposed to the sun and then into the house to radiate the heat into the space. And it could be through the floor, it could be through wall radiators or other devices. Next slide, please. Now, when it comes to generating electrical power, as I mentioned, there's concentrating solar power, and then there's photovoltaics. In concentrating solar power, we're working specifically with the heat of the sun. Two main categories of concentrating solar power are trough systems and power towers. A trough system is going to refer to the shape of the reflector, and we'll show a slide of that. And then photovoltaics are a different approach. So let's go to the next slide to look at more concentrating solar power. Here we can see a kind of a dish situation here where we're focusing the light. These troughs would track the sun, and you can imagine, because of the convex shape of the reflectors, that the rays of the sun would, thank you there, would focus to a focal point where there may be a tube of liquid sodium or some other fluid that would collect that heat and deliver it to a different part of the power plant and potentially convert that heat to steam. If they produce steam, then the steam could drive a turbine connected to an electrical generator, and that would be one way. We call it, we also talk about solar thermal plants because they're dealing again with the heat. Another approach to that, next slide, please, is this idea of a power tower. You may be able to make out down there towers in the center of these areas that are, these areas down here are covered with individual mirrors down on the flats. And you can kind of make out the bluish color, like thousands of individual, they're called heliostats, helio for the sun, and these are all tracking the sun. And what they do, and you know, in the Mojave Desert, it's sunny most of the time, most of the year, and they're getting the sun, and they're concentrating it up to the top of the tower. At the top of these towers might be a fluid. Again, it could be liquid sodium, it could be other fluids, that is going to become superheated and then delivered again to a generation plant that will take that heat, transfer it, create steam, spin a turbine, which spins a generator, creating electricity again. This installation says it uses 347,000 garage door sized mirrors. That's remarkable. Next slide, please. Now, photovoltaics, and Karen knows I'm a solar photovoltaic nut. I love it. I've been fascinated by it since childhood because there's no moving parts here. It doesn't depend upon the heat of the sun. It simply transforms light, radiant energy, light energy into electrical current. And it's really outstanding, and it's really kind of fascinating how it works. If we go to the next slide, I'll explain a little bit. A photovoltaic cell consists of two layers, an N layer and a P layer, and that refers to the charge, the negative or positive character of that material. The material may consist of any number of different combinations of elements, but for the purposes of this discussion, we will assume that silicon is the primary material used, and that we are using what's called doping. We're adding a little bit of an additional element to the top surface or N layer, and a different element to the bottom layer. And what we look at is, you can look at the periodic table to find what is it that would be what would be a good candidate for the element to add to the silicon to give it a negative character. And if we put a little bit of phosphorus in with the top layer, phosphorus has one additional electron when compared to silicon. Silicon has 4 electrons in its valence in its outer ring. It's a very stable material and a very stable atom. And if you add a little bit of phosphorus, you kind of upset the balance of that wafer, of that layer, with a little bit of extra electron energy, like a little a negative. You give it a negative character. And at the same time, at the bottom layer, if you what they call dope it by adding a little bit of boron, for example, boron is to the left of the silicon column. It has 1 fewer valence electron. In other words, it has in its outer shell 3 electrons compared to silicon's 4. So we set up a kind of an imbalance of charge where the upper layer that faces the sun has a few extra electrons, and the bottom layer that's away from the sun has a few is what you could call electron holes, some empty spots. And what happens is, if we provide a current, we connect a wire or create a circuit from the N layer to a place where some work can be done, and bring that back to the back side of this solar cell, and then expose the cell to light. What will happen is that the photons, the energy of photons coming from the sun, striking the cell, will provide enough energy to free some of these electrons, the energy from some of these electrons in the negative charged layer, to actually create an electrical current. And that current will come around to the backside where there are electron holes, and there's kind of an appetite for free electrons. And at the same time this is happening, electrons will naturally drift back up to the N layer, and you get this constant cycle as long as sunlight is striking the solar cell. If there's no sun, there's no current. If there's no circuit, there's no current. So the things you need are a circuit, an opportunity for some work to be done. It could be a motor, a battery, a LED bulb, something for that energy to do. And you need the circuit to come all the way to the backside of the solar cell, and you need the light source striking it. And what these are called, these are semiconductors, and it's very closely associated with the same technology that gives us a light emitting diode, and the whole semiconductor industry that runs our electronics these days. It's a semiconductor. It's a solid state energy creation device. Light into electricity. Next slide, please. The smallest element in a solar system is a cell, and they can be anywhere from a size of a postage stamp to maybe 4 inches square or so. What we're used to seeing, anything larger than a calculator, is a solar module or a solar panel, what you see being installed on roofs. That's a module. It consists of several cells wired together in series and parallel to produce maybe 12, 24, 48 volts direct current. These produce direct current, which is like a battery in your flashlight or an automobile battery. It has a positive and a negative lead. And when you put, if you're building a system on a home or larger, you would have several modules. And when you put together several modules, that creates an array. Next slide, please. This diagram would be representative of an off-grid standalone photovoltaic system. Working from left to right, a solar module or a solar array creating direct current energy is going to be connected to a charge controller and a battery. You would not want to connect directly to the battery because you could overcharge the battery. So the charge controller is going to do a few things. It's going to make sure that you can't overcharge the battery, but it can also become a central location for distributing a DC power to, say, your light bulbs and things. If you were on a boat, for example, you could have a low voltage or a DC system that ran your direct current, low voltage lights, radios, and so forth, and keep your battery charged. If you want to run AC devices and alternating current devices like, say, a home radio or a toaster or something, you're going to need an inverter. And what an inverter does is it takes direct current power and converts it into alternating current, which is what our household, typical household wall outlets use at 115 volts alternating current. So an inverter converts power, but this is a standalone system. This would work. You could be miles away from any electric utility company, and this would work. Next slide. We see a lot of uses, and North America, because we are kind of a large area, we have there's a lot of remote standalone use of photovoltaic power. I have no control over that dog. I'm so sorry. I will try to. Millie? No, I'm sorry. So in remote locations, these could be train crossings, power stations that are remote, science stations that are remote. You might have a standalone PV power system. Millie, I'm so sorry. I live alone. I don't have somebody, and I thought maybe I could put her in the car doing this, and usually no one ever comes.
Do you want me to take over while you go get her?
Why don't you take over? I'm so sorry.
Sure.
Thanks.
That's okay. So this graphic here is just showing the top countries that have installed photovoltaics. As you can see, China is the leader. China's been installing a lot of different kinds of electricity generation. Germany is right up there. Germany for a long time has been offering a lot of tax incentives to their citizens to get as much renewable energy going as possible. They would like to be carbon neutral, and they would like to get rid of all their nuclear power. So that's a big ask of such a small country. So they have a lot of incentives. As you can see, the United States is third in installed capacity, but pretty neck and neck with Japan. In terms of growth, the solar industry and the solar generation has been growing tremendously in the last 10 years. If you just go 10 years ago, well, this is going up to 2017, so let's go 10 years back to that. 2007, very little solar energy installed. And so now we're at over 400 gigawatts, excuse me, and China being the one that has really come on the scene in the last 5 years. So solar energy has what we call a lot of ups and downs, pros and cons, advantages and disadvantages. So the things that are really great about solar that we really like about it are that it's clean when you use it and sustainable. As long as the sun is there, you can use solar. Sunlight is free, and we can get electricity basically anywhere the sun shines. So that's really helpful. The disadvantages are that solar panels tend to be a little less efficient than other sources of energy. And of course, the sun is not out all the time. You have rainy days, you have cloudy days, and you have significant hours of no sunlight at all at night. So where you are is really going to factor heavily into whether you can use solar energy in your house. I grew up in Michigan, And the state of Michigan in the month of January has virtually no sunlight. It's very cloudy and overcast almost the whole month of January. And so solar in January in Michigan is not such a great idea, but in Arizona, it's an excellent idea. And then when you purify the silicon that goes into solar cells, the purification process does produce a little bit of heavy metal waste. Anytime you purify anything that came out of the ground, you're going to have some other stuff left over. And so that does have an environmental impact. We want to make sure that whoever is purifying that silicon and making those silicon crystals for those solar cells is doing so in an environmentally responsible way. So now what we're going to do is we're going to talk a little bit about energy management with solar energy. You cannot just slap a bunch of solar on your house and then use energy willy-nilly, because your solar system is not going to produce as much power as you need it to. So this is an up-close picture of a device that is really helpful. It's called a kilowatt meter. You can pick this up in your local big box or hardware store for, I don't know, 15 or 20 bucks. If you look for it on sale, it might be less than that. And you plug devices into it and tells you how much power each of those devices uses. And it's really handy, and I really like it. So when you're looking at installing solar energy at your house, you want to make the most of the energy you can produce. Most of us are limited in space or in budget to how many solar panels we might be able to install at our homes. And so if you're limited that way, you want to make sure you're going to make the best use of it. So the first thing you want to do is you want to analyze your energy use. You want to take a look at your utility bills, see how many kilowatt hours you're using every month, and see if you can look for ways to reduce your energy consumption. By reduce your electricity use, I have 3 ways here. There's more, but these are the 3 big ones. If you go through and invest in energy management measures, so we're talking about making sure your house is as airtight as is practical, making sure that you have maybe some smart controls like a smart thermostat, some smart light bulbs that you can control through an app on your phone, things of that nature. And then also utilizing things like passive solar and efficient lighting, those kinds of things. So you're minimizing the amount of electricity that you're using while installing and using things that are relatively inexpensive compared to the cost of, say, 2 more solar panels. Then take a look at your HVAC system. HVAC is heating, ventilation, and air conditioning. And your heating and air conditioning is the #1 energy user in your home. And so if you can get that at a more efficient level, you will save energy, you'll reduce your carbon footprint, and you won't have to have as much solar installed. And then your other appliances like your electronics, your refrigerator, your dishwasher, your washing machine, those kinds of things. Then once you've done all those things, kind of taking a look at the technology in your home, take a look at how you use that technology, energy conservation behaviors. You're going to want to learn to use less energy even with what you have. So I have an old refrigerator at my house. I don't need to leave the door open. Even though it's a less efficient model, I can still use it in a wise way. Then once you've done all that, you can take a look at your energy use. You're going to size your system to that lower energy use. And also you want to make sure you're anticipating any needs. If you're planning on buying an all-electric plug-in vehicle in the next 5 years, you want to make sure that your solar system will accommodate that and you won't have to pull as much energy off the grid. You might decide you want to install something like a power wall or a battery bank to store energy to use in the evening or when it's a cloudy day. And so you just want to make sure that your system is the right size. You don't want too big because you're overspending, and you don't want too small and say, oh, I shoulda, coulda, wish I woulda had a bigger system.
Yep.
Okay, so the next thing to take a look at is your devices that you're using. We call this energy efficiency. How much energy does the equipment in your house use? One thing to look at is the Energy Star logo for electronics and appliances. The Energy Star logo indicates devices that use the least amount of energy to accomplish the same amount of work. Then you want to take a look at how big your refrigerators and freezers are. We tend to think bigger is better, but if you're 2 people, you do not need a 36 cubic foot refrigerator. If you're buying a really, really big refrigerator and only keeping it half full, you're using a lot more electricity because that empty space uses more energy to keep things cold than if it's full of food. You have things like power strips and smart power strips that will help minimize the amount of electricity you use, that you can turn off the whole power strip, or a smart power strip will sense when you turn off a device and then cut power to everything else plugged into it. Then you can have smart home technology, like I mentioned before, like a smart thermostat, LEDs that are Wi-Fi ready. There's all kinds of stuff. We're calling it the Internet of Things, things that are linked together, you know, your Alexa that's controlling everything, those kinds of devices. And then lastly, but probably the biggest bang for your buck, is going to be switching all your lighting over to LED lighting. That is going to, first of all, those light bulbs are going to last a really long time. And secondly, it's going to make a big dent in your electric bill and your electric consumption. So once we've looked at the devices that we have, we're going to take a look at our behaviors. And we want to adapt to using less energy through behavior. This is energy conservation. So take a look at your thermostat settings. Can you make the heat at a lower temperature, or the air conditioner at a higher temperature at night, or when everybody is gone for the day? Are you making sure that you're opening and closing the blinds appropriately? Opening those blinds and drapes in the winter time to let the sunlight in and warm your space, closing them in the summertime so that the sun isn't making your space too hot. And then you have things called phantom loads. Phantom loads are power loads that are being pulled by devices that look like they're off, but they're not really off. And two big tells are, if you see an LED light, you know it's using power, like your microwave clock, or if it has a remote control or can start with a remote device like your game system. Those things have some power consumption all the time because they're waiting for that signal from that remote. So if you take a look at all of these things and analyze that behavior, you'll be able to keep your electricity consumption low with or without a solar system. Okay, so the next part of our presentation is we're going to talk about building a solar cooker. We have a little bit of a competition for you. And so we want to talk about building a solar cooker, what goes into building a solar cooker, and then give you some examples and then get you started on that. You can buy solar cookers commercially. They look a lot like this, or it's a kind of an insulated box. Some of them are insulated plastic. Some are cardboard that's insulated. There's wood. I mean, they're all different kinds of construction, but they're all going to have some sort of insulated box. They're all going to have some place where you put the food, and they're all going to have some kind of reflector. And then you need a thermometer to tell you how hot it is inside that commercial oven. When we build our own solar cookers, we're going to model them after that setup. So you want to make sure you have a reflector. You want to make sure you have insulation. You want to make sure that the interior is black, so it's absorbing as much of that radiant energy as possible and changing it to thermal. And you want to make sure that your oven is airtight. You don't want to heat up the air and then have the air escape. So you want to make sure that you have that space airtight. So we have a couple of examples of solar cookers for you. This one uses a Pringles can. So you can cut a hole, poke a hole in the metal end and in the lid, and send a skewer across there and cook like a hot dog, or maybe string a bunch of marshmallows on there. And so you can do that just by cutting a couple flaps in a Pringles can. That's a fast and easy way to make a solar cooker, and it's kind of fun. And you also get to eat all the Pringles before you make it. So this is what one looks like when it's completed. You want to definitely make sure that you keep the hole that you cut for the sunlight to go in covered with some kind of plastic wrap. You can use clear tape to do that, or you can tape a piece of clear saran wrap over the top. But you want to make sure that once you put that lid on, that it's airtight so that that hot air stays inside that Pringles can. The Pringles can is not extremely well insulated. So you want to make sure it's nice and tight so that it's going to cook that hot dog or cook those marshmallows for you. Another way that we have seen people make a solar cooker is with a pizza box. Use a new pizza box. Don't save one from your pizza last night because it'll be greasy and gross. Okay, so you just kind of cut a little flap in the lid, like a picture frame, or cut out a picture frame out of the lid, and then you use that as your reflector and where you tape your plastic wrap. So that flap that you kind of cut out here, you're going to then bend that flap up and cover it in aluminum foil, and then you cover that hole with plastic wrap. and then you put the black paper on the bottom of the box, and that is where you're going to put your food. And there are a couple little places, a couple little holes that you need to cover up with tape also to make sure that there's no air escaping the pizza box. But this is you're gonna use this for something low, like corn chips with cheese on it to make some nachos, or chocolate on a graham cracker to make a s'more. And there's the black paper on the inside of the box, so that when you close the lid to the pizza box, it looks like that. And then you can use a skewer. We have a bamboo skewer there over on the edge to kind of prop it up if you don't want to hold it in place. Because the idea is to get the angle of that reflector such that it's bringing more sunlight into your solar oven. So I'm going to quit screen sharing for now. And Barry and I have a couple of examples of solar ovens. So Barry, why don't you grab yours and I'll get mine ready.
I have one here. It's a standard pizza box oven, and the same as you kind of described. You can see the lid flips up and is covered with foil. I have a skewer that I would use to, and some holes, carefully placed holes here that I could use to make sure that when I'm out in the sun, I get just the proper angle on, because you want the sun to be, and you just move this around and you can tell when the sun is shining brightly and reflecting directly into your cooking area. There's saran wrap, I think you can tell, keeping the oven area sealed, and that is taped from the back side to the hole that I cut open. I have black paper all the way around. And I realized this morning when I dug this out of my solar oven closet that there are some things I could have done to this to make it better. Actually, earlier I had spray painted the box white because I wanted to get rid of the advertising for the pizza company. I would make this would be a hotter box, a better oven, if I had painted it all black. So that's something I could have done, or covered it in black paper. I could also have added any kind of insulation, including bubble wrap, around it. That might have made it, and then paint it black. So I didn't actually take advantage then of painting the outside black, and I didn't take advantage of the possibility of using insulation. And if I wanted to make this even more efficient, I could probably add a couple more reflecting panels on the left and the right side. Pizza box oven.
Excellent. So this afternoon I put one together from an Amazon box. Now that everybody is at home and ordering in, we have a lot of Amazon boxes sitting around. I made a little oven door on mine so I could get my food in, and I don't have black paper at home, so I used black cloth, and I put little latches on it so my door would stay shut and would stay airtight in there. And then I used the flaps, and I used a cereal box to make this top. Okay, so here's my plastic wrap. And then I covered my lid, my flaps, and my cereal box pieces in aluminum foil, and they reflect sunlight into the box. Now today here in central Indiana, the temperature was about 48 degrees, and I got the interior of my solar oven up to 122 degrees at 3 o'clock this afternoon. So not too bad. The sun is pretty low in the sky. It was kind of breezy, and I was still able to get it warm enough to make a s'more. So my snack today was a s'more made with my solar oven. And so that gives you a couple of ideas, a couple of ways that you can make them. So now what I would like to do is go back to the PowerPoint, click back here. I want to talk to you about our solar cooker contest. Our contest, we have a contest for you with valuable prizes. Okay, so first of all, you have 3 steps, okay? You need to build a cooker. You can do the Pringle can one, you can do the pizza box, you can do your own design. We want you to use repurposed materials, okay? So remember the key parts. You need a reflector, it needs to be able to it needs to have a dark interior. You probably want to insulate it. I did not insulate mine and it did okay, but if you insulate it, it'll be better. And you want to make sure there's a way to get light in there, so a clear top. Then you're going to use an oven thermometer to test your cooker. See how hot you can get the interior of your solar cooker. You want it to get as high as you possibly can. All right, when you have the highest temperature you think you can get, you're going to take a picture of that thermometer inside your cooker registering that temperature, and you're going to email it. We'll give you that email address here in just a second. You're going to email, that's your entry. Your entry is a picture of your solar cooker with that oven inside showing us how hot you got that solar cooker. Okay, so here are the rules. Contests always have to have rules, so here they are. First of all, you need to make it from scratch. You cannot take a commercial or a pre-existing solar cooker and tweak it and say, okay, I'm done. You have to start over, okay? We'd like you to use repurposed materials. Now, clearly your plastic wrap and your aluminum foil and your tape are not going to be repurposed, but we'd like you to take things that you already have in your recycle bin. Kids, check with your parents first before taking stuff. We'd like you to repurpose your materials, okay? Hit that recycle bin up, find some things that are in your house already. Don't go buy new stuff. The oven thermometer should be inside to show us the temperature. We want to have that, when you take that picture, make sure you have that solar cooker outside in the sunlight with the oven thermometer. So it's what we call in situ, or where you would use that solar cooker, okay? 1 photo per household. So if a couple of you are working on it together, you'll submit 1 entry. You can build as many as you'd like, but 1 entry per home. And then your submissions need to be received no later than the end of the day Friday, so 11:59 p.m. Eastern time, Friday night, to the email address I give you in a second. And then on Saturday, we're going to have a little half-hour celebration and announcing of the winners of the solar cooker contest. There are prizes for first, second, and third place. And these are prizes you want. These are not prizes that are, it's not a half blown up balloon. These are things that you want. Okay, so you need to be on that Zoom call with us Saturday. How do you enter? Take a picture of your solar cooker with that thermometer inside. Make sure we can clearly see that temperature. Make sure we can see that. If I have to enlarge it, that's okay. Make sure we can see that. Give us your photo with your name, address, and phone number if we have to call you. You're going to send it to my email, which is right there in that blue-green box, cterrell@need.org. cterrell@need.org is the email, and we'll keep that up on the screen here for a little while. Then you need to, if we want to win, you need to join us on Saturday. We're going to give you a Zoom link. So you email us the picture. I will reply to your email with the Zoom link to have for Saturday morning so that you can join us to celebrate your solar cookers. We can talk about the pluses and minuses. We're talking a half hour out of the morning, guys. It's not going to be all day. And then we will announce the winners, and we'll make sure you get your prizes, and then we will enjoy the weekend. And you can go make some more s'mores or some more nachos or whatever you're making in your solar cooker. Okay? So if you have any questions, Barry and I are glad to answer them. We'd love to have you get started on working on those, but I know it's just about 7 o'clock. So I want to be respectful of your time and make sure that we can get out of here exactly when we want to, but that is the email, cterrell@need.org. That's the email you need to make sure you email those pictures to enter your solar cooker to win, okay, by the end of the day Friday. So if you're on Pacific time, it's going to cut you off, but your sun goes down earlier than that anyway. We wanted to make sure that you had time to test your solar cookers when the sun is actually in the sky. So we're going to have you start building it and get started on it and have a good time with it. And then send us a picture testing it, and then we'll get back together as a group. I'm going to stop screen sharing. Then Barry and I.
Thanks, Karen. And yeah, you would want to be trying to build this, have it done tomorrow so that you could take advantage of Friday's hopefully sunniness to get your high temperature. There's no limit on how long it sits outside. If you're lucky enough to have sun, get the highest temperature you can. As Karen said, each household can build more than one oven. There are dozens of directions and suggestions on the internet you can go and look for. And as Karen mentioned, hopefully it would be out of repurposed materials. But anybody can build a successful solar oven. Anybody can build an oven that can at least make s'mores. And we hope everyone will participate. We really look forward to seeing the entries. And once we have the entries and we have the winners, or even if we have all of our entries, we might want to get pictures of your designs, pictures of you, pictures of the creator with your ovens, beyond the award-winning temperature shot. So we just really look forward to that. Karen's provided her email, and she will answer any questions that you have run up to this.
Okay, great. Thank you very, very much, Karen and Barry, for that presentation. Outstanding. Really informative, really interesting, really hands-on, and helps you all at home be able to make your own nachos from the power of the sun. How good is that?
Right.
So I'm sure people can come up with all sorts of ways to, all sorts of things to cook and all sorts of snacks to make there, among other things. So thank you so much for that presentation. Tyler, I really want to go over to you, my colleague who's in the back round, to see if there are any questions that have come in for Karen and Barry before we sign off for the evening.
No, I think you guys anticipated and answered all questions that our audience may have had. Just did get a few thank yous from those that are in our audience, but otherwise, I think we're all set.
All right, I look forward
great.
to getting
Thank you
those
very much.
photos and finding out how you guys do with those solar cookers. It'll be great.
Me too. I look forward to seeing y'all on Saturday.
All right. Well, thank you. Yes, thank you to my colleague Tyler. Thank you very much to all of the participants, and we will look forward to seeing the results of the competition and what people are doing out there with this newfound knowledge. And thank you again to Karen and Barry for sharing their time, their expertise, and their obvious interest and passion in what they do. We want to just give our thanks to both of them and to Need for their time this evening. So with that, that concludes our session this evening. Do return on the third Wednesday of December for the student showcase, where we will hear from 6 different student projects concerning clean energy. So with that, we conclude tonight's program and sign off for a clean energy. Thank you all.
Yeah, thank you.